Hello everybody, welcome back to the Calculus Examination Preparation course. In the last lecture, we have talked about the calculation of the derivative or the differentiation operation already. So in today's lecture, we're going to further look on the other methods, which is very powerful to help us to find out the derivative for the complex formulas. Alrighty, let's go. Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists, an positive number m. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than m, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here, like this one is called a, okay, it's called a, around at the point x0. So it means if we choose the neighborhood of x0, right, defined by the formula here, okay, this is like x0 minus delta, this is like x0 plus delta. So in this region, now we have the f(x) in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, yeah, it is correct, because on this point it is 5, on this point is 7, and now on this point is even lower than 5. So you can say that the function's value is also within a certain range. So we can say it is locally bounded. Yeah, locally bounded. Okay, so how can we prove this? Okay. Alrighty. So we have done the taking logarithms on both sides of the function equation. However, we cannot see the derivative. Yes. So the next step for us to do is to do the differentiation operation on both sides of the equation. So we're going to have this one and okay, right? Alright, let's try it. Now for the line y, it's very simple from our table, okay? But remember, y is still a function of x. So this is actually a very simple looking compound function. So remember, we have to put a y prime here. Okay, so for the right side, it's going to be easy too. So we have this. We have, remember, the minus x's derivative will be minus 1. So that's why we have to put minus 1 here. Okay? Alrighty, let's go. Alrighty, so finally we just have to, put a y on the right, and on the left we only have the y prime left. Okay, so we can have something like this. Okay, and y, we understand that equals to the line, sorry. Just put a y back as its original form. Okay, so that's it. Well, look at how complex the result is. If you're going to use the regular, the basic operations of the derivatives, it's going to be too complex for us to find the result in time, especially during the examination. Okay, so we have learned the three very important methods for us to find out the derivatives. So how about we try some integrated questions? So the first one is about, okay, we'll see example. Okay, so we have this. It looks, weird already. It's about a derivative of, to y. Okay. Okay, so I want you to show something. So show. Okay. So the second order derivative, but remember this is x2y. Okay, equals to and also we have third order derivative of x2y, which has the form okay. Well, some students may get a little confused about this one. So let's see how to show this one. So this one is actually derivative from the regular, derivative of the function y to x. Yeah, we write it like this. So however, if you just make the invert of this, we're gonna have, okay, this is no question. See, that's just it is. Okay, so let's start from the second order operation. Okay, so we have dx dy, but this is second order. Okay, second order derivative. So for the second order derivative, it has a bridge with the first order. For the first order, we have something like this. Okay, so on a, the base of the first order result, we just have to do the differentiation operation again, like this. Okay, so this one, if we want to find out the further result of this operation, we have to do some equivalent conversion. Okay, let's see. Yeah. However, this time we'll have this. So we can take advantage of the result we got previously. This one, right? And do the derivative of it. And for this one, it's just this one. Okay, let's continue. So here we have 1 over y prime. And here we have another one as, okay, so for this one, now we understand that it's, it's within the derivative table, it's a very regular, power functions derivative. So we can have it as right, okay. But remember that y prime is still a function of x. So this one, although it looks simple, but still a compound function. So we have to do something here. The prime's prime will give us, yes, double prime. Okay? So let's simplify it. So finally we're going to have y prime's third order with a denominator as y double prime. Okay, so see, we have already proved the first equation. Awesome. So let's continue with the second one. Okay, so for the third order derivative, we have something like that. And we can further convert it to the derivative of the second order derivative, which means on the basis of the second order derivative, we can further write it down like this. Okay, so no problem, right? Okay, let's try it. So here, we still have to do the equivalent conversion here. So let's, put a dx here. And of course, we have to put dx here to cancel it out. Okay. So on top, we have this one. Okay. Let's expand it. So the result we have we got just now is the minus y double prime divided by the y prime's cube. So we can put it here. Okay, and dx over dy is the derivative of x to y, first order. And we have the result as 1 over y prime. Alrighty, so for the first part, this part, we understand that it is a based division operation of the derivatives. Okay, so here we can have it as, okay, because this one equals to, from the table we understand that, right? That's why we have to do this, okay? Sorry, I forgot, okay. On top we have, double prime times prime cube, but minus the minus y double prime times the y prime's cubes derivative. Okay, let's further simplify it. Okay, let's look at it. So on the bottom we have, the basic power operation. So we can just put it down like this one. Okay, so on top we have, this. Double prime's prime will become triple prime. Okay. And also we have this guy here. Okay, so we have 3 times the y prime square, and also we have to do the prime. Always remember, y is a function of x, so that's why it's a very simple looking compound function. Okay, so this one can, be further simplified as, okay, okay, so since we have a, double prime here, so that actually we can put them together. Okay. And further, because we have the y prime here, y prime here, and y prime here, y prime here. We can cancel some y primes out. And finally, we're going to have this one. Okay, so that's the the final form. See? Yeah, we have it here. So this one has been proved too. Okay. Okay, so the next form of the derivative operation I want to talk about is about the parameter equation. So what is it? So usually we have the function expressed like this, right? However, sometimes we don't know the direct relation between y and x. So this time we can, express it as this. So we all understand the relations between x and the medium we call t. X, y, and all have expressions, relations with t. So this time, we have established the indirect relations between x and y. Okay, so that's why we call the t as the parameter. Okay, called as parameter function. Okay, called a parameter function. All right, so this time, let's look at one example here. So for example, we have x equals to line e plus t squared and y equals to t minus arc tanning t. All right, so we have the relations, function relation between x and y expressed with its parameter functions. But now our question, of course, is to find out the derivative, and also it is to find out the third order derivative. Okay, so in order to find out the third order derivative, we have to find out the first order derivative first. Well, similar to the operation called the equivalent conversion or deformation we had last time in the number 4 example, we have to introduce the dt. Well, to have the dy and dx all have relations with t, with the parameter here. Okay, so that's why we can further express this. Okay, so this one is the derivative of y, to t, and this one is the derivative of t to x. We understand that this looks kind of weird, so we want to convert it to dx divided by dt. So this time it's just a regular derivative operation about t in this equation, or in our case in this equation. Okay, so let's try the derivative of this dy to dt, this equation. So if you forget, please refer to the derivative table. Arctangent t's derivative will give us, okay, yes, because t's derivative will be 1 and arctangent's derivative will become this one. Yes. All right, so on the bottom we have this guy's derivative, which is going to be, okay, so we can cancel out the denominator here. Okay, so finally we can have okay, so that's the result for the first order derivative. All right, similarly we can do the second order derivative like this. So we said that on the base of the first order derivative, we can expand the, such form as such form. We're gonna show here. Okay, so to have, both the y and x to have relations with the t, because we're using the parameter functions. So that's why we have to do similar conversion, equivalent to conversion as. And this one can be further converted to Okay, since we understand that the dy to dx is t over 2 from the last calculation, so we can just put it here, the t over 2 is prime, and divided by the derivative, first order derivative of x to t. So this one is going to be ln. Okay. Alright, so let's continue. So the t over 2's problem is very simple. It's just 1 over 2. What about this one? This one is, we have calculated last time, actually. It is this. So this one is one cancelled out. So finally we're going to have, I'm sorry, it's not cancelled out here. It just means because this 2 is actually on the denominator position, so that's why we have this actually. Okay, so we have found out the second order of the d for the between 1 and x in a medium of t. Okay, so in the same path, we can have the third order derivative as okay. Well, so this one we already find it out, for this one, which is 1 plus t squared divided by 4t. Okay, but before that, let's do the same equivalent transformation first. So which can be further write down like this one. Please follow me if you can. Okay. Alright, so this part we have been using it over and over again. Okay, what is it? Cool. It's nothing but just 2t over 1 plus t squared. What about this one? This one is on the base of this one. Okay, so it is the derivative of this t function. Okay, so let's try it. So for this one, we have 16 squared, okay, and 1's prime will be 0. Okay, so we can't forget about it. So we have 2t plus the 4t here, and then minus, the 1 plus t squared times 4, okay? And then divided by this whole thing. Okay, let's simplify it a little bit. So this one will give us 8t squared minus 4 and minus 4t squared. Okay, and divided by this and this. So this one and this one canceled out for a little bit. And we have the 4 canceled out here. Have this and this canceled out here. So we're going to have t squared minus 1 divided by 2t squared divided by t divided by t squared plus 1. Okay, so let's change it to okay. So now we're gonna have okay, so we can actually put everything together like this, and finally we're gonna have this. Okay, so that's all the 5 methods we're going to talk about for the derivative skills. So I think you have mastered how to use the parameter functions to help us to find out the derivative, for regular function y equals to fx. So now, do you want to try something by yourself? Okay, here it is. Okay, so the practice. Okay. So we have this one. So find out the second order. And also I want you to find out the specific value of the derivative at t equals 0. Okay, find it out. Okay, you can pause the video and maybe give yourself 20 to 30 minutes to try this. Okay, did you pause the video? Okay, let's try the, find out the solution together. So similarly, in order to find out the second order derivative, we have to find out the first order derivative. And we have to, add something, do the equivalent transformation to have y and x all have connections with the parameter t. Yes. Okay, so just in case, some students forget or are confused about how to do this, now we can do it again. So we just put a dt here and a dt here. Yeah, and further transform it as okay. So now you can just do the regular derivative on y and also on x, which are all the parameters t's function now. Okay, so let's write here for the y prime, we're gonna have cosine t, right? And also we have the 1 plus et. Okay, so this one is very easy. We don't have to spend too much time on it. Okay, so now let's get on to the second step, which is about to find out the second order derivative on the base of the first order derivative. Okay, so we still have to do the transformation to have everybody x and y to have the relations with the parameter t. Okay, all right, here I'm gonna have this guy, as we can see that it is cosine t divided by e t to the power of t, and then to the prime. And then of course we understand that dt to dx is this. Okay, because we actually, calculate this one in the last step. So we can just put it down, write it down like what it is. So this one is actually, can further write it down like this one. Okay, so that's why, that's why we can just write it down like this. Okay, so for this, for the left part, this is about the, the basic division operation for the two derivatives, for the divisions derivative. So be careful, we're gonna have 1 plus et squared, okay? Gonna have this sine t times sky, and then minus, yes, cosine t times the, okay, the 1 will be gone, and I'm gonna have et left. Okay, let's reorganize this, because this one and this one are actually the same. So let's put them onto the denominator as a whole. So we're going to have the e plus the et, okay, the cube. And on top we have minus xt, t, and then minus cosine e to the power of t. Okay, let's be careful. So that's the result basically for the second order derivative of y to x. So what about when t equals to 0? So what is the specific value of this derivative? Okay, let's put the t in. So the t is going to be 0, right? So we're going to have e plus e0 cube. And the sine t is going to be 0, of course. And, because this is going to be 0, 2, so this is going to be 0, 2. And the cosine t, it's going to be 1. Okay, 1 times the e to the power of 0 is going to be 1, 2. So we're going to have 1 plus 1 here, and here we have minus 2. At the bottom, we're going to have, I'm sorry, this was still the minus 1. Yeah, have 8, top we have 1. So the minus 1/8. Okay, so now we can answer the question. The derivative, second order derivative, about y and x is minus 1/8.